My name is Pauls Bartins, and I'll be presenting a new Metamodel specialization-based domain-specific language approach to deep learning lifecycle data management. It consists of a very simple but universal deep learning lifecycle data management core tool, still usable in practice, and an advanced extension mechanism that converts the core tool into a DSL tool-building framework for deep learning lifecycle data management tasks. The deep learning process naturally requires the ability to track, compare, and reproduce the experiments. While machine learning tools and libraries have matured, with some trying to automate parts of the process, manual experiment running is still commonplace. Good tool support is essential for productivity. Similar solutions on the market limit the user to visualizations provided, not allowing custom extension of the program. They are also often commercially closed projects. The tactic is to try and provide all functionalities that could be needed, but you end up with a massive tool that tries to do all, but for real tasks still misses some functionality. Our solution consists of three main parts: Core Tool, which is a simple deep learning lifecycle data management tool stored on a data server; a core library, installed on the workstation of the deep learning expert. It sends messages to the data server; and a core extension mechanism stored on the data server allows extension of the bare bones core tool to great levels of customization. For extension, Metamodel specialization is used. When accessed from a web page, this is what the core tool looks like. Once logged in, you have access to your projects, as well as the option to create new ones. Under each project, you can upload or view training and test data, as well as see its runs. A run is created when a Python program, augmented with our library functions, sends your login credentials and calls a start run. The run then contains all the messages and files logged to the server after, through using the log and upload file functions. Finish run is executed at the end, so the server knows the runtime of your program. Under the hood, the projects, runs, and logs are structured as can be seen here, in the core logical metamodel. On the server, all files are stored under a shared ancestor folder following this repository structure. For extension, we use a metamodel specialization technique developed by some of the authors in past papers. First, we define the universal metamodel for our domain. Then, a specialized metamodel can be defined for each use case in the domain. The specialized metamodel contains a set of subclasses of the universal metamodel classes. There are two ways to allow extension to our program. One would be to reveal our codebase, but that will be complicated and unnecessary for the user. Instead, we reveal only crucial parts, easily understandable, but still relaying all needed information on internals. Logical metamodel, the repository structure, and the Mongo database structure, where the core logical metamodel and its instances are stored. There are two supported extension types. Sense classes are for giving specific roles to messages or files. These are then used to organize the logs and the output, as well as how their storage is structured. In the specialized metamodel, runtime and accuracy would be specialized versions of literal with general sense, the red arrows, meaning the log message is displayed with the relevant title. Loss pairs is a specialization of literal with /pair sense, the orange arrow. This allows recognition of the fact that a pair of values are being logged and displays and stores them accordingly. Code, checkpoints, and silver captions are specializations of files with sense pointer, the pink arrow, which again displays the files with the respective title. The more hardcore extensions are the custom tabs. There, the user can write their own code that is called with the run or project ID as parameter. The result of the code is displayed in a new browser window. This opens many possibilities for types of extension, which can use any of the stored data from project runs. An example is the gold-silver view. It takes uploaded silver captions file and puts it in a table next to images and gold captions from the testing data, giving a custom fit table perfect for progress tracking in an image captioning task. The metamodel specialization would look similar to how I described it for sense classes. In the web page resulting from specialization, the buttons for calling the tabs are located here. To summarize, our offered lifecycle data management framework is based on the idea that by means of specialization of the mentioned extension classes, we will define concrete deep learning lifecycle data management tools which provide new additional possibilities in comparison to the core platform. For sense classes, we apply simple specialization, while the heavyweight deep learning DSL tool building facility is a specialization of custom tab classes for which we apply a new type of specialization, functional specialization. These classes have an attribute program name, which, after specialization, must point to an independent executable program, the extension program. Thank you for your attention. Are there any questions?